welcome to a special space-themed edition of Science Solution Santa Cruz. This is a deep dive episode, and if you've seen one of these before, you know that a deep dive episode is guest hosted by Eric Palkovacs, who's the director of the Institute of Marine Sciences at UC Santa Cruz. And since Eric is a scientist, he gets to sit down with a fellow scientist, and they really geek out on this stuff. And so today, Eric sits down with X Prochaska, who is a distinguished professor of astronomy at UC Santa Cruz, who has recently moved into ocean sciences. So he went astronomer to ocean science. And so Eric and X totally geek out on how X and his team are using tools that normally measure galaxies and using them to measure what's going on in the ocean. They dig into how AI plays into all of this, and they even hatch a new project, and they scope out a new project to create a digital twin of Monterey Bay right here on the show today. So this is a super geeky, space-themed episode of Science Solution Santa Cruz. I'm Jonathan Hicken. Enjoy.
Welcome to another deep dive episode of Science Solution Santa Cruz. My name's Eric Palkovacs. I'm the director of the Institute of Marine Science here at UC Santa Cruz, and it is my pleasure today to welcome distinguished professor of astronomy and astrophysics, X Prochaska. Welcome
pleasure.
To the
Thank
show.
You. It's great to be here. I've been to the Seymour Center probably at least 10 or 15 times.
Well, welcome back.
Thank you, but never behind the staff doors, so it's nice to see what goes on back here.
You got to come in the secret side door this time.
I did, right?
Yeah. So let's start out by talking a little bit about your background and your interest in science in general, right? So it's not sort of the usual thing to have a professor of astronomy talking about marine science. So let's talk a little bit about how you got into science in general.
Right on. For sure, the spark, or the spark that really got me going was my high school physics teacher, Crandall Dimmick, Mr. Dimmick, who I still interact with. I met him in person in Rhode Island. He's just past 70 years old. But he developed what was in me into a real, young scientist, very young scientist at the time. Yeah.
And are you interested originally in space or just...
I was.
Yeah.
I would read Scientific American before high school. Not all of it. And one of the articles that really spoke to me were cosmology. So understanding the universe on the biggest scales.
And so as you your scientific interests sort of evolved, what kind of astronomy questions were you asking?
As a PhD student at UC San Diego, down south, in physics, we were studying how galaxies assemble, how galaxies like our own Milky Way come into being by looking back in time a few billion years after the Big Bang, about 10 billion years 10 billion years ago.
Right.
With the brand new Keck telescopes, which are kindly funded by our taxpayers.
Tell us a little bit more about those tools, the tools that you were using to do that work.
So for most of my thesis, I used what we call the high-res spectrograph in a shell, which splits up the light into really the finest of colors, built here at UC Santa Cruz.
Okay, cool.
At Lick Observatories by Steve Oat, my colleague. That instrument's about the size of this room. It sits at the Keck telescope in Hawaii in Mauna Kea. And we used it, myself and my PhD advisor, Art Wolf, to study distant quasars. So peculiar objects, supermassive black holes that aren't dark. In fact, the opposite. They're super bright.
Huh.
And we could use the light from those objects, quasars, which accidentally went through a foreground galaxy to study that galaxy.
Okay.
In silhouette. So most of my science, my whole career actually, has been science in silhouette.
So this is kind of like also sort of the discovery of exoplanets when they sort of traverse across like a star.
That's a good analogy. Same scientist, Steve Oat, same spectrograph, high res, same telescope, Keck. The first 100 exoplanets were mainly with that instrument in Hawaii. And instead of directly imaging exoplanets, they were able to infer their existence from the signals, some of the changes in the light that they were measuring.
That's right. And I heard recently that they could even measure clouds or detect
Yeah,
clouds on exoplanets.
Another silhouette idea, not with that instrument. Probably first done either with the Hubble Space Telescope or Spitzer. Not important. But as the planet rotates, it's the signal you collect with those satellites varies, and you can infer the presence of clouds. Or if a planet goes in front of the star, you can actually infer something about its atmosphere from the way it modulates the star's light.
Right. So what can you learn about galaxies as they go in front of these quasars?
So galaxies like our own, especially back in the early days, are mainly gas and dust.
Uh-huh.
And both gas and dust imprint signals on the light that's passing through them.
Uh-huh.
And we can get very precise. We can actually measure the chemical composition of the galaxy. Many of the elements of the periodic table would appear in our data.
Okay.
And as well as dust, the dust reddens the light that's traveling through it.
Okay.
And so from the color of the light, you can learn about the dust in the system as well.
And are you ultimately interested in sort of things like the age of the galaxy, or like what are the fundamental kind of...
As a physicist, it's mass. It's always mass.
Okay.
And everything actually kind of correlates with mass.
Okay. So now to go to sort of you've made a career pivot, and we'll make a pivot in this conversation, right? Which is to say that now you've kind of changed or pivoted a little bit in the questions you're asking as a scientist, to be asking questions about the oceans now, and kind of turning some of these tools that you use to study distant galaxies towards asking questions about the ocean. So can you say a little bit about, like, first of all, what inspired your change in kind of in the whole system you were interested in studying?
Right. So I grew up in Rhode Island, where I went to high school with Mr. Dimmick, where the Graduate School of Oceanography lays. In fact, I was married in the church right next to GSO, Graduate School of Oceanography. I started my first research project as a college student was in oceanography at URI in one summer.
Okay.
And I considered it for a PhD, but I didn't do it. So it lay dormant for about 20 years. And in 2020, or close to that, I saw a pair of my astronomy projects about to complete. They never really finished, but to reach a level where I was comfortable to walk away from them.
Okay.
And decided what would I do next. And AI had arrived for me in those days. This was early.
When was this?
2017, give or take.
Okay.
Quickly appreciated that AI is not a great tool for astronomy. We use it, don't get me wrong. But AI really sings when you present it with very complex data.
Okay.
And a lot of the data we astronomers collect are dots, and you don't need AI for dots.
Okay.
You need AI for biology. You need AI for complex processes, turbulence. You need AI when you don't have a great existing language to describe the phenomenon.
Okay.
So as I was an early adopter of AI and realized the science I was doing was not well suited to it, I decided I would bring back the oceanography.
Right.
And then throw AI at it because I could. Yeah.
It can handle these massive data sets.
It can handle massive data sets, yeah. And actually, conceptually, bring a language to processes that we struggle to put a language to as scientists. And a great example, we have a word for eddies.
Uh-huh.
We have a word for fronts. But if I show a picture of sea surface temperature or ocean color from a satellite, it's full of information that we can use that word, but it barely captures anything that's going on. That's when AI sings.
So how do you view, to kind of get a little philosophical about the process of science, right? This is kind of the role of theory, right? Is like kind of establishing a model for how the world works. And then we go out and as empirical scientists, we go out and test that theoretical model and ask, how well does it predict what we actually can measure in nature? So you're sort of saying, like, in the sort of AI is helping you develop sort of fundamental theory about what processes are occurring out there. So almost more like an iterative process of observing and developing theory kind of in this iterative process.
And that's a great way of describing how astrophysics is done.
Okay.
Model built on usually in the computer these days. Confronted with data,
right?
Often killed. The goal of an observationalist is to kill models.
Right.
Coming back briefly to your question about the mass, my PhD thesis was to infer the masses of these galaxies.
Okay.
We killed the existing models of the day and got in a lot of trouble for it. But that was how you make progress.
And then were they replaced by new models that describe reality better?
Correct.
Right. So, I mean, that's the ultimate goal.
That is how science develops. I found oceanography does a little bit less of that, and for good reason. In astronomy, for good reasons, it's rare in astronomy that the models that we're developing are useful, other than describing the universe.
Right.
But a lot of oceanography, the models my colleagues develop are useful. They tell you where to fish.
Yep.
They tell you when you wish they can tell you when a heat wave's about to hit.
Right.
Or an algal bloom might turn on. And so you're building those models for other purposes. And still you want to confront them with data to improve them. So
right.
we do.
Yep.
But there's actually a lot of different emphases in that scientific process compared to what goes on in astrophysics.
So to get into the details a little bit, so you've been studying this thing that you refer to as ocean color. So you can say a little bit about what is ocean color.
It's well described. It's what an astrophysicist calls spectroscopy. So that spectrograph high res that I mentioned, that was my first science as a PhD student. In oceanography, spectroscopy is called ocean color.
Okay.
And it's literally splitting the light that we receive from the ocean to its many colors. And like astronomy, one of the main applications is to infer what's in the ocean. In astronomy, we infer what's in the galaxy, as I described.
Yep.
Or in a star. For the ocean, we use its color to infer the biology that's within it.
So you need not just the observations of ocean color, but you probably also need some data as to what's going on under the waves to know kind of, oh, hey, this is what we see in terms of ocean color. What is this signaling to us about the life in the ocean? So you need some other data stream as well.
It is, yeah. It's a we would say somewhat degenerate problem. That is, different biology can give you something close to the same color. That makes it a hard problem.
Okay, yep. Can you give an example of like two different processes that might generate the same color signature?
I'll give you an easy one, which is detritus, aka dead stuff in the ocean.
Right.
And colored dissolved organic matter. Well named, but a mouthful. Colored dissolved organic matter, CDOM.
Okay.
Have almost the same absorption spectra.
Okay.
That is, they will absorb light in the water almost the same way.
Okay.
That makes them almost completely degenerate.
So the inference or the sort of why might we want to be able to separate those things and understand which is which?
Yeah. I assume your listeners are aware that sequestration of carbon is an important concept these days. That is the removal of carbon from the atmosphere into the ocean.
Yep.
Detritus is a primary way that process is done. Things die and sink to the bottom.
Right.
So you would love to know how much detritus is both at the surface of the ocean. Ocean color can help.
Right.
And how much of it sinks to the bottom. That's a harder problem, actually.
Okay.
So if you miscount how much detritus is there by orders of magnitude, which you can, you've got a lot of uncertainty in that process.
Yep.
The flip side, CDOM, the O again in CDOM is organic, also carbon, biology, a lot of biological processes at play.
Yep.
Which we care about in the ocean, not even including carbon sequestration, but also just the growth of life or the feeding of our planet. So being able to assess CDOM is vital for a number of other processes as well.
Okay. So is this a common thing you encounter where you might have different ways of getting to the same sort of color signature? Is this like a problem that you're sort of actively like, oh man, this is a critical issue, or is this kind of a rare situation?
It's probably rare. It is. I think it's still rare, but it's forefront of my mind.
Okay.
I'm today launching a project to try and solve it with AI.
Okay.
It's such a hard problem.
Okay.
And I don't know if I will.
Okay, well, we're going to come back to the AI conversation specifically, so we'll dive into that one a little bit in a second.
Yeah.
The data streams you use, can you tell us a little bit about what are the data streams that you're actively using? So you've got ocean color data coming from where? What sources? What's measuring it? State
of the art today is NASA's PACE satellite. PACE is an acronym: phytoplankton, aerosols, or atmosphere. Color, something experiment.
Okay.
That's a $1 billion mission to measure the color of both land and sea.
Okay.
It provides that information every 1 to 2 days over every kilometer of Earth. That's the global coverage. It does make a pass over Monterey Bay once every 1 or 2 days.
Okay.
However, that's kilometer resolution's a bit coarse for coastal processes.
Yep.
So your listeners probably are aware there's many sensors in the Monterey Bay. One of the ones I take advantage of is a glider that goes back and forth from the bay out 300 kilometers from shore.
Okay.
And back and out and back every couple of weeks. It has about 10 sensors on it. Temperature, salinity, chlorophyll fluorescence, velocities, dissolved oxygen. We're adding pH. The community's adding pH, phosphorus. And I know I'm missing 1 or 2 others. Backscattering, and maybe one other.
Okay.
And so that collects data in Monterey Bay every time it comes in and goes back out. So
Right.
every couple of weeks it makes a pass.
Okay.
To depth, 500 meters. No, maybe 1,500 meters.
Okay.
And gives us in situ, in the water, in the ocean, observations of what's going on.
And that you complement with the satellite data.
Correct. Which only, with ocean color, only gives you the upper tens of meters at best.
Okay.
Of the biology that's present. I think I can say now I'm an expert in sea surface temperature, also collected from satellites. Measures the temperature of the ocean right at the surface.
Okay.
As in the upper 10 microns.
Upper 10 microns. Okay. Very surface.
And that's it.
So based on what you've studied with the glider, how much does that tell you about temperature at depth?
When I give a public talk on climate crisis, one of the early slides I show is the increase in energy in the ocean to depth, not just that upper 10 microns.
Right.
And I'm going to misquote the number. It's in the unit of zetajoules. The first time I looked at that slide, I didn't make it. I had to look at what zeta was. I still can't remember what order of the power that is, but our behavior has pumped in zetajoules of heat over the last 50 years. And we know that because of these, in this case, it's floats, not gliders, similar device called Argo, which are across the planet. There's several thousand of them. They profile to the 1,500 meters,
right,
measuring the temperature as they go for decades now, which you need to do to assess climate. And we can measure very precisely how much energy we've dumped into the ocean, not the surface, the ocean.
And of course, there's like natural processes too that change ocean temperature,
Absolutely.
right? The one that's been in the news a lot recently is the so-called like Godzilla El Nino,
which my close colleague is working hard on.
Have you? Yeah. So tell us a little bit about how do we know that this Godzilla El Nino is developing?
A combination of satellite measurements, which again give the upper surface only, but global, so we can see what the temperature is throughout the Pacific Ocean, which is ginormous. That makes it very clear that the temperature at the surface has warmed this year substantially, especially in San Diego. I think it's probably got to us by now. But El Nino is a heating event in the equatorial Pacific, so on the equator of the Pacific. Again, you can see that from satellite directly. But we also the community, have floats, these Argo floats throughout the Pacific Ocean, which give additional information about the warming of the Pacific. And then Dan, my colleague at Scripps, runs gliders off of San Diego, the one I talked about from Monterey, one off Santa Barbara, and one to the north of us. And the one in San Diego also makes very clear that the water there has warmed anomalously, and we're in the midst of some kind of Godzilla, as you call it.
I mean, I remember past El Ninos or predictions, let's say, of El Ninos that sort of were never fully developed, or it was like, oh, we're going to have one. And then it's sort of like, oh, we're not so sure now. And then it was kind of like, oh, well, no, it never really happened.
Prediction's hard.
Hard. Ultimately that would be to sort of reduce the uncertainty in these predictions would be huge. Absolutely. Right? I mean, so is this something you're thinking about?
I'm not a modeler. Let me start with that. I'm more of a data collector and then confront models. I think about it in that respect, but I don't think I'll be building the model.
Uh-huh.
But I agree with you that as humans, the capability to build those models is highly impactful. But as I said twice, it's hard. It's really hard. That's why you've heard of examples of where early in the year there were suggestions El Nino would be big that year, and it wasn't.
Right.
'Cause it is hard.
Do people look back and say, this is a year when we thought that this was going to happen and it never happened?
Sure.
What were the misleading signals?
They try. That's hard too. It really is. For a number of reasons. One, the Earth is large, and we have, as I've somewhat emphasized, very few sensors in the water. We can measure the surface well. We do.
Yep.
But in the waters, it's generally expensive. Floats are not that expensive. Nevertheless, you can only put so many floats in.
Right.
Even if they aren't that expensive. So measuring the ocean's hard. Measuring the atmosphere is easier, and we do that better. I think as a result, we humans are better at forecasting the weather than how the ocean's about to evolve in that given year.
Uh-huh.
The physics is well known, but except this is a big but turbulence, which actually lies at the heart of lack of human understanding in many fields, including astrophysics.
Uh-huh.
So because that's so difficult to model and predict, that's where we frequently fall down into being able to model the ocean or weather or the interior of a star or the formation of a star or the collapse of a gas cloud to make a galaxy. Turbulence really is hard and limits our knowledge, our ability to predict.
You know, if you haven't visited the Seymour Marine Discovery Center at UC Santa Cruz in a while, or ever, you really should come visit us. We are right on the bluffs of the beautiful Monterey Bay, with an aquarium full of local species and a bunch of hands-on science exhibits that help you understand what's happening in our ocean and along our coast. We are connecting the incredible research happening at UC Santa Cruz with real-world solutions for our coastal community. We don't want science to just sit on a shelf. We want it to shape decisions, inspire kids, and help our community feel equipped to act. So if you care about the future of our ocean and our coastal community, or you just want to experience a place that makes you feel a little more connected to it, come visit us at the Seymour Marine Discovery Center. Science Solutions, Santa Cruz.
The fact that you're thinking about these common processes, right? I mean, like what's happening in galaxies, what's happening in the ocean, you're making those connections between sort of these fundamental processes. I mean, I think one, that's really like, it's kind of amazing that these physical processes are occurring across such different scales. I mean, we think about oceans as being big, at least in the realm that I operate, which is biology. I think about the ocean as being big, but in your sphere, actually the ocean's pretty small compared to like the known universe, right? So, but I don't talk to a lot of scientists who are connecting things across these scales and looking for commonalities and processes across these scales. And, you know, as we think about kind of the future of science, I mean, how do you think about, like, as we train graduate students, postdocs, should we be training people more broadly to think across these scales, seeing that sort of this has sort of been a hallmark of your career?
I'll go with yes, but I'm biased heavily because you're talking to a physicist,
right?
And the arrogance of a physicist is that we feel we can jump into any field, and because physics underlies what's going on, not have impact, but at least have some understanding.
Right.
So that's a way of saying maybe.
Yeah.
There's great value in interdisciplinarity.
Yeah.
Across the sciences probably as well. But I think first and foremost, learn how to read. Learn how to do logic. Learn some mathematics.
Yeah.
Learn some science. That level of interdisciplinarity. Learn some art. Learn how to sketch your ideas. That is more important than us educating, at least at the undergraduate level,
right,
humans across science disciplines.
I mean, it does seem though as things get more specialized, the language gets more specialized. In many ways, it gets harder. It gets less accessible, right? So even if you're a graduate student in oceanography and you want to learn a little bit of cosmology, it gets pretty inaccessible pretty quickly because the language changes. So do we need some interdisciplinary training? Like, I know you have some interest in teaching across more broadly across these things. Is that something we should be doing much more of?
Can I pivot to AI?
You absolutely. Let's pivot to AI. I know you're dying to talk about AI.
I don't know if I'm dying, but
well,
it's the right answer.
All right.
That
How
question.
can AI help us?
AI is a polymath.
Okay.
I've written but not yet published, so you're getting the first public announcement. AI now surpasses me as a scientist.
Okay.
I'm pretty good in two fields right now, oceanography and astronomy. It surpasses me in both. I would assert it surpasses every scientist in every one of their fields today.
And so
That
when you
is
say
a polymath.
surpasses, how so? Like in doing what tasks specifically?
Research, first and foremost, which I guess is my bread and butter.
Uh-huh.
I'm not a great instructor. At least I don't think I am. So I can't even assess if I'm sure it's better than me in instruction because that's not my bread and butter. But let's stick with research. Yeah, it outperforms me in every task of research except data collection. And I think our time is only limited there as far as robotics.
So for data, so say a little bit more about that.
The data sets you were describing. Somebody had to build the satellite, put it up there.
Yep.
AI is not doing that
Okay.
today. Someone had to build the glider, put it in the ocean, refurbish it, take it out, refurbish it. AI is not doing that today. Somebody goes and counts seals. People are now
Right.
building
Automating some
systems
of
that
that.
automate that. So
Yep,
data
yep.
collection is where humans still have a leg up.
Okay.
That's it. I can't think of anything else today.
There was a paper that came out recently maybe in Nature about AI's impacts up to this point. So you're kind of talking about where we are at this very moment. This paper was a little more retrospective, right? And I'm not sure, I don't remember the authors, but the idea was AI tools are quite good. And by AI in this paper, I think they're referring to kind of, machine learning tools, which have been around for some time. Okay. Very good at like refining fields or like digging deeper into existing fields, but not so good at spinning up new fields, like brand new fields that was where kind of there wasn't a lot of AI contribution.
Fair enough. Yeah.
At least historically. And so if we know the question,
I'm happy to speak to that.
Well, let's say if we know the question,
Yep.
you can unleash AI and maybe get a pretty good answer. But what if we don't even know the question yet?
That's hard. That would be a hard one to answer. Let me answer that question a little bit this way. Astronomy, data driven. Always has been. It's always led theory. Oceanography, amusingly, I think theory led the way to an extent that still boggles my mind. Partly because I know data collection is very expensive in oceanography.
Yep.
It's expensive in astronomy too, to be honest.
Yeah.
But always been data driven. Oceanography now, I think today is data driven.
Okay.
So if you've got to collect the data to make your understanding,
right,
and AI can't collect the data, what I just emphasized, then it is hard to launch new fields because you're not collecting the data.
Yep.
As soon as we have tools that will autonomously collect the data, I'm willing to bet we will push into other fields or wherever you were describing in ways that we can't today.
Yeah, because it's sort of like you need to envision why those data sets would be important. You have to sort of say, what's the reason? What's the justification for even collecting those data? Right. You kind of need an original reason to do it. And if that's the foundation, I mean, I think this does kind of get to the structure of science in some ways, Absolutely. Right? And it's like, how does theory and empirical science, how do those interact? And I think as science has become more data driven over time, as data has become more available, it's become more data driven. The theory has become more data driven, essentially. So you only see that accelerating.
Right, and let's be clear, the scientific method is confronting theory with data.
Yeah.
It's probably too strong a statement. I don't know if you can do science just with theory.
Well, you need to test it somehow.
To the extent that data is required, that's
right.
a limiting factor today to AI having that next level of impact.
Let's talk a little bit about your local work in Monterey Bay and maybe what specific questions you're trying to answer with that work.
Right on. I'm part of that glider effort that measures Monterey Bay every couple of weeks.
Yep.
And continue to take advantage of some of that data. But I've been funded by the Simons Foundation to pivot into oceanography by the Simons Pivot Fellowship.
Aptly named.
Yes, indeed. About half of the funding I've received from Simons will be devoted to a project to measure the ocean color and the sea surface temperature of Monterey Bay. Ideally every day. That's ambitious. With a UAV, a drone.
This is like an aerial drone.
Absolutely.
So it flies like a grid over Monterey Bay.
That's the current concept.
Okay.
Perhaps launch from right here at the Seymour Center.
Okay, awesome.
The dean promised that I could buy myself a container and put it on site. That's what I've been granted so far.
All right, can we be there when it takes its maiden voyage?
Yes, we intend to do a test this summer. We will do a test this summer. So that's the data collection.
Okay.
The science is twofold. Temperature for many oceanographers triggers the word physical oceanography, but not entirely. And then ocean color definitely triggers biological oceanography. So ocean color is about learning what's in Monterey Bay. And how that evolves.
So we're talking phytoplankton.
Absolutely. Phytoplankton, detritus, which is dead stuff. Algal blooms, usually often a form of phytoplankton, which can be harmful to us and our wildlife in the Monterey Bay. In principle, and I think in practice, you can measure ash and pollutants that we put into the ocean. River runoff from intense storms, all sorts of things can change the color at the surface.
How long are the drone flights?
Yeah.
How long does it take to fly a drone over Monterey Bay?
Right on. So the drone that I have my eyes on today, built out of Colorado, has a duration of 2 hours.
Okay.
I would, at the very least, have multiple battery packs to do multiple flights per day. With enough funding, I may have multiple drones as well. And let's see, I think it travels of order 50 kilometers. No, it must be more. 150 kilometers in that 2 hours.
Okay. Can you observe the whole bay in that amount of time? Not quite.
Not certainly not with one, not with two. With four, it starts to get close.
Okay. There's this idea out there, I'm sure you're well aware of like digital twin.
Mm-hmm.
What about creating a digital twin of Monterey Bay? Is that idea out there? Should we put it out there?
I know who to ask, which would be folks at Mbari, but
because it's
I
like
know.
if we had all this information, right? Yeah. Shouldn't we put it into a digital twin? I mean, the other thing, what's cool is all the research all the other research that's happening on Monterey Bay. We've got so much instrumentation in Monterey Bay detecting kind of the location of individual animals. Mm-hmm. So it's like all the way from physics to biology. We could really make a sweet digital twin.
We should.
Yeah,
that's a great idea.
Yeah.
I will be at the Monterey Bay Aquarium Research Institute, Mbari, in 3 weeks. If it's okay, I'll start suggesting it.
Let's do it.
They have the resources.
We have the expertise.
We can help a little bit.
Nice. Yeah, that's awesome. Originally, I want to come back to a point you made when I asked about pivoting from looking up at the sky to looking down at the ocean. One of the things you said was we can answer some practical questions by looking down at the ocean and some things that actually can, that sort of people care about, like what's going on with fisheries or like what's going on with climate. Say a little bit more maybe about, how you hope to impact those areas, like maybe fisheries in particular. What kind of things might we be able to learn about fisheries? Just because that's my own interest, right? So I'll go in my own direction.
I'll answer it this way. One of my colleagues here at UC Santa Cruz is Chris Edwards.
Okay, yeah.
Probably appreciate he runs the regional model of the ocean state.
Yep.
For coastal California. He builds that model. That's a sophisticated model that does predict the state of the ocean some number of days out. That model takes as inputs the glider data I've described.
Yeah.
A bit certainly some satellite data, float data, ship data. I would love to integrate drone data into that process. We could maybe even run a finer, very local regional model to predict the state. And when I say state, it's the temperature of the water, the salinity of the water, both of which impact fish.
Yep.
What Chris and his team have added to that model a bit is biology. They've started adding in phytoplankton and like organisms.
Right.
Fish eat, whales eat phytoplankton.
Right.
So to the extent that they can add that to their model successfully, then they can start predicting where phytoplankton will be and grow and die and evolve on our local scales that would absolutely impact fisheries.
Right.
That would be the direction I would push and am pushing, to be honest.
Okay. And you mentioned climate as well.
Yeah.
What do you think about climate impacts on our ability to either like predict the impacts of climate change or the time scales over which different aspects of climate change will manifest? What are you thinking there?
And I call it climate crisis because it is.
Right.
Climate's a slow process. Even slow on the scale of a human lifetime. It's about the same. That is to say, you need to measure for decades to first understand what's going on, or have some understanding. To to sink that in. We all appreciate, well, not so much in Santa Cruz, but there are seasons out there. There's some parts of the
some
country.
parts of the world there are seasons.
Actually experience a winter and a summer. So there's seasonal effects that change the ocean on seasonal timescales every couple months.
Yeah.
You have to understand that first.
Yeah.
There are annual effects. El Nino is a great one.
Yeah.
That you have to have some understanding of before you can look for decadal effects, which is climate.
Yep.
So the glider network I'm describing to you is one of the few experiments that's been in the ocean long enough to make something sensible about how the ocean's changing on climate scales.
And how many decades has that been?
More than 20 years.
Okay.
Satellites have been up for about 30 years now. They too are therefore have a long enough data set to say something good about, something valuable.
Longer term,
how climate is changing.
Yep.
There are ship programs. I'm sure you know of Cal Coffee.
Yep.
So we the community have run ship tracks, they call them, off of California for decades.
Yeah.
So that too is an experiment where you can say have had enough data to say how things are changing slowly on decadal scales, climate scales.
Yeah.
So that's a long way of saying we have very few data sets on the planet that measure climate well. All the atmospheric things have existed for decades because humans care about weather. Those are great too.
Yep.
The CO2 monitor that the current administration is trying to kill in Mauna Kea, that's a 50 or 60 year experiment.
Yeah.
But you need to go that long. And human attention time span is rarely that good enough for that long.
And the tools kind of change too over time, right?
That doesn't make it easier.
Yeah.
Actually, it's harder.
I mean, in fisheries, it's interesting, right? Because there's always this debate about modernizing sort of fishery independent sampling. And there's always these sort of argument and counter argument, right? The counter argument being, we have some data sets of trawl nets going back a long time. Those are super valuable just because the tool has been deployed in the exact same way for a really long time. True. So, why replace that with eDNA if now all of a sudden we're like not sure how the two things line up? And I guess the idea is sort of maybe one could do them both for a while.
Would like to do them both for a while
and
Absolutely.
See how
be able to hand off.
Yeah,
if you can.
Exactly.
Absolutely.
But it is
that's happened in space as well. So,
okay, how has that happened?
The example that comes right to mind is we have the ability to estimate sea ice around Antarctica and the Arctic in particular.
Yeah.
And there have been 3 or 4 satellites over the last 30 years doing that. So one mission dies and no one picks it up. The community tries to have overlap so you can hand off one to the other. But there's been some failures in that, which have led to some inflammatory articles in Nature about what sea ice has and has not been doing in Antarctica.
Okay.
Because of how hard that problem can be.
You had mentioned, or you had wanted to talk a little bit about AI, and we kind of talked about it for a bit, but I know that you have some thoughts on kind of how AI might influence science and society at large, sort of big picture. So how do you think our jobs as scientists are going to change over the next let's only say 5 to 10 years, because out longer than that, it probably becomes pretty hard to predict.
5 is already far enough.
Exactly. So how do you think, how will our jobs on a day-to-day basis be impacted by AI over the next 5 years?
Dramatically, in one word. Disruptive for sure as well. More negative. I'm trying to estimate your age from your looks. I think you're about my age, but 5 years for us, I'm retired anyways. So it's not affecting me at all. Well, it's affecting me today because it's the power boost I suddenly have.
Right.
But long term, it doesn't matter. I'm irrelevant. The impact on the youth is huge. And it's not a good time to have such a disruptive force.
But does it mean that like scientists need to be just fundamentally trained in a different way?
It will. Yep. But that's just one piece in the puzzle. I worry more about the money, the funding.
Like the funding
of the current generation of scientists in this country.
Yeah.
I should say, let me preface, I think the rest of the world will handle this better than the United States.
So in terms of what is it important to maintain funding for in particular?
If the United States wants to have scientists in 20 years, they need to maintain funding for young scientists.
Yeah. Yeah.
Full stop.
Well, we certainly do. I mean, it's part of the reason most of us get into this job in the first
we certainly,
place.
Absolutely.
That's an important piece of what we do, right?
I'll add a story. Hopefully Jimmy Panetta doesn't yell at me. A group of astronomers went into his office a year ago when the federal government was already turning up the heat or being as disruptive as possible.
Right.
To express our concerns.
Yeah.
And he got it, but of course they were doing a billion things at once. So we weren't high on his list of concerns. And shouldn't have been. But the one thing that I think finally the message that did get across was it wasn't going to hurt my career. Not because I'm about to retire.
Right.
But because I've survived. We've been in a constrained funding environment for 30 years.
Yeah.
You take away half my money. Okay, it's 2 times harder. What do I care? It was already friggin' hard.
Yeah. Right.
Right. But you take away 2 times the money, you just eliminated half the PhD students.
Right.
That's a big deal. And so I got part of that point across and said, in fact, I'm advising my students, don't stay in the United States. Why do you want to have to fight tooth and nail for a PhD when Europe will fund you fully or Asia will fund you fully?
And of course, it's sort of an own goal, right? Using
Absolutely.
A World Cup analogy. Is that it's like it's our own competitiveness that's at stake here, right? And our own ability to predict what all these things we've been talking about, like the future of fisheries. We could be doing much better at understanding what they are, and that's jobs, and that's coastal economies. And by eliminating our ability to do those things, ultimately it's hurting not just the scientists, it's hurting all coastal communities.
Preaching to the choir.
Well, it's been so great to talk to you and wonderful to learn about a whole suite of things that I don't usually think about on a daily basis. And just thank you so much for being on the show.
My pleasure. Thanks for having me.
All right, that does it for today's special, extra geeky, space-themed episode of Science Solutions Santa Cruz. So thank you to Eric Palkovacs for guest hosting today. Thank you to X for coming on, and thank you to both of you guys for geeking out on space and galaxies and AI and even scoping a new project right here on the show. Thank you to Edith Belmont for editing. Thank you to Carrie Goodbar for production. Thank you for listening. We'll see you next time.